very soon everything will be streamed. Window capture. Okay, so we're back now. Yes. Okay, but you know, and on the dates in the wiki, you will have the recording. So now there is recording of previous year. I will change it with this recording, unless the lecture is a mess for some reason, and then I keep the old link. Yes. So so lectures on Tuesday morning, 9:30. So the grading formula is 35% on homework, 35 on colloquium, 30 on exam. So homeworks, there is regular deadlines because it's like a course, you cannot learn it in the end. Like it's growing a muscle a little bit, get used to the definition. So it's better to work regularly. Therefore, regular deadlines every odd lecture. But of course, today is no deadline. Since the second lecture is in 2 days on Tuesday, so this is just to start a course in time, you understand, right? That means that first deadline is on the 2nd of October before the lecture. So you should think 1st of October, otherwise you need to work the all night. Yes, and the homework, some homeworks have extra problem, and I add the score to the exam. And so the idea is if you solve a few extra problems, you have good score. Colloquium, I mean, if you learn everything, you have 10 out of 10 for colloquium. And that means that on final exam, many students are already very close to having maximal score for the student. I mean, sorry, I say many students. It's like one student a year, but now there are more students. So maybe this year, 2 or 3 students. So if you do everything more or less correctly, then you only need 6 out of 10 for final exam. So it's open book. And normally it's very easy to have 4 out of 10 for exam. But if you did all the homework and colloquium correctly, 6 should be easy. And you don't need to come because I believe you can do this. Yes. Okay, and the rest I said. So a colloquium, so the list of questions you have 2 weeks in advance, but then I will be very busy, so you need to pressure me to give you the list. Yeah, just do it. Otherwise, okay. Yes. Any questions practically? So seminars will be online and the link should be on Wikipedia before the seminar. I didn't check it. So I will replace the slide so that you have the updated practical information.
That exam is used every year, is that right?
Sorry, you can use all the lecture notes.
Yeah.
So so basically all the links you have on the wiki. So I can only see on your screen the wiki. Oh, okay, some dictionary, like some people want to know a word in English, it's okay. So Google Translate or something is okay, or Yandex Translate. Lecture notes, and you can bring handwritten notes. So if you prepared some homework task or some colloquium thing and you want to, it's okay. So personal handwritten, yeah, personal handwritten. So it's okay, but I need to see and that's handwritten, and then I will check your writing and think whether I believe it's yours or not. So if I see 20 people with the same your copies of your notes, and then yeah, there will be a problem. Okay. But don't worry for exam because they're just questions. If you make homework, then you won't need anything at all. And I mean, almost nothing you need. So, okay. So let's start with the lecture. Oh, there is something happening in the chat. Yeah, the seminars are after the lecture. So this one at 11:40, hopefully maybe a small delay because we have a few lectures, and on Tuesdays also the same. So yeah, it's not yet in maybe there is still a mess in rules. So yes, indeed, good question. Thank you. Okay. So this lecture, I try to make each lectures two part of 40 minutes. First part is philosophy. Second part is, okay, overview of course, what is the goal and so on. Why is it important? Well, it's maybe not so important, but okay, how might it be important? And then I will speak about online mistake model. So this is important for seminar. And let us check the time. Oh, so I should be a bit faster. So, okay, first goals of statistical learning theory is that we get some data and we want to construct a mapping from inputs to outputs. So inputs always curly X, outputs always curly Y. And so it is so there are different branches in machine learning and statistical learning theory, and we will mostly speak about binary classification, but we will need to speak about regression a bit later in the second half of the course because they're connected. But the main goal will be to study binary classification just for simplicity. Clustering and dimension reduction, that's probably going to be in seminars or homework, exam, and so on. It's your task to generalize the proof techniques. So then I will skip like other branches because I guess you know this from machine learning course. So so in batch learning you receive all the data at once. So that will be most of the course except the first 3 lectures where we speak about online learning. So part 1 is the but there is also active learning, so where the learner can choose the inputs. So if you want to learn a threshold function, it's convenient. You can do binary search. Unsupervised learning, clustering is just you get a bunch of points and you have to identify which points are similar, and you don't get any labels. So this is usually if label data is expensive, you want to do some preparation, like construct some hypothesis, like what might be the class, what might be similar. So anomaly detection. So there is you remove data points that are very different in the hope that learning algorithm will work better. So, but okay, so anomaly detection, you also do an IQ test. So on the right, you see a question from IQ test. So one is different from the others. And so you can think about which one. Okay, and then there is intermediate, semi-supervised, and transactive learning. There is also a big field on reinforcement learning, which becomes more important for tuning parameters and all the other algorithms. So there is an agent and a reward, an agent and environment that gets reward. So these fields, they are studied in this field statistical learning theory. Okay, so there's also classification or regression is also studied in statistics. But what's different between statistical learning theory is that in statistics, you will assume specific distributions on inputs or inputs and outputs. So you say family of Gaussian distributions or whatever. And then you construct estimators. So in such a, here there will be no assumptions, like no strong assumptions. We will not say our inputs are from this family. We just say any probability distribution. So in second part, we will have no assumptions. On third part, we will have margin assumptions. So, but this is a very vague assumption. So that's still almost all distribution, just excluding, just there is between the two classes, there is a margin and there is a lot of space between. So we exclude inputs near the margin. We say it's clearly inside the region of one label, inputs are there. Or let's say the probability of seeing a point there is quite small. Otherwise, okay, and also the goal is to make bounds on the performance of the algorithms. So we will study half space classification, and we will say this algorithm is guaranteed to work well. Whenever the underlying, whenever data is generated, that labeled data is generated according to a half space. But the distribution on input can be arbitrarily difficult. Okay, so so the idea is by learning this theory, you get like deeper understanding of algorithms. So if you skip this course, so then you will be equally good in tuning parameters. And so for many people, I don't know about you, but most people who work in IT, they're just tuning parameters. So you don't need a theory. But but if you want to do research, it's pleasant to have some ideas what's happening and maybe some clues of explanation why it works. But the problem is that very little is known why things work. So what I try to do is explain the basics of the best explanations. Okay, so yeah, but at the same time, let's train a little bit mathematical problem solving so that you can get used to the concepts, learn about the main ideas. And so the effect is that for thesis or something, you will need to read paper from ICML or NeurIPS or something. And they start, usually most papers start with some theory part. And so if you know this theory part, then implementing the algorithm should be easy. Like if you have certain questions, should I do this loop in this or this way? If you know the theory, you can think, okay, probably he knows this. Or if you have the source code, and then you can understand a little bit why he does certain thing in certain order. Okay. So let's start. So let's explain the goal of the course with some example, and just also prevent some highlights. So there exists one nearest neighbor algorithm. Maybe you already know what it is. Okay, I will repeat. And we'll also speak about hyperplane classification. So there's linear SVM. Maybe you also know about this. Yeah, the fourth year student know about the third year, not yet. So, okay, so let's think about our first task. I moved the bar a little bit. So we want to fit half spaces. So here you see a square, and the inputs are pairs of real numbers between 0 and 1. And there is white points and black points. So well, actually, I have circles and squares. So bullets and squares. So bullets are in the white area and squares are in the black area. So we don't. So here you see, like we will assume there is a true classifier, so that labels for training and testing are generated according to this white regions. But we don't know this white regions. What we get is a bunch of data points. And so now we need to choose a half space. So we know that the border is a line, and we need to choose a line. So we can choose this line, for example. Our algorithm, whatever it is, chooses this line. So here I put the true region back, and then there is some region where our algorithm makes a mistake. And so we are interested in this mistake. Okay, it's inverted the color, so there are two regions where we make a mistake. Okay. And so we will prove a theorem that regardless how we fix a line that's consistent with our training data, the probability that the test point belongs into to the error region. And so, and also regardless what is the distribution and the square of inputs, probability that a test point is in the error region is very small as soon as we have a few points in our sample. So this is for 2 dimensions. It's not so impressive. So, but in D dimensions, the number of points we need is linear in D, like 10D or something. And then we will also have like a test error 0.1 or 0.01. Then you need like 100D or something. So yeah, so it is D divided by epsilon. If you're ordered D divided by epsilon, if you want to have error probability likely to be below epsilon. Okay. So we can deploy our algorithm to fit half spaces, but we might be in trouble that the true hypothesis is not a half space. So the white and black area is more complex. And then fitting half spaces is a problem. So if this is the true hypothesis, then any half space we fit, it will have error at least 1/4, even a bit more. So how can we see this? So we can divide the input space in squares with with size 1/2. So this disjoint is partition of squares of 1/2. And for every line that we fit in 4 points, we know at least 1 point is misclassified. So so here I assume uniform distribution on input, sorry, yeah. I assume uniform distribution and error probability of a line will be at least 1/4. Actually 3/8, but it doesn't matter now. Okay. So we can use another algorithm called one nearest neighbor algorithm. So how does it work? So when we get a test point, we will look to the closest training point and predict the same label. So this is one nearest neighbor algorithm. And so here you see that's called Voronoi diagram. So the cells are all the points for which its training point is closest. And so that's the decision border that we get. And so here are the 2 examples. The right one is our example for half spaces. And so this has certain properties, like all points on the training set are correctly classified by one nearest neighbor algorithm. Because if you check, okay, that's clear. Okay. So it looks like it can, so you can prove it approximate any smooth classification, any smooth border between the classes. But not always working well. So I thought about the counterexample, and here is a counterexample with hypercube and D dimensions. So there is a center that has probability 1/2, and with probability 1/2, we take the input is a point of a hypercube in D dimensions around the center. And then it turns out that before nearest neighbor algorithm starts to work, you need a training set S. So in the bottom is a training set of size at least exponential in the dimension in this example. And so this is a consequence of Chernoff bound. I will skip the proof now. And so it will be easy exercise. So when we review about probability in lecture 3 or 4, it's an exercise. Okay. And so I did another experiment to study a problem with one nearest neighbor algorithm. So I took now a box. The inputs are t-dimensional box. Coordinate, absolute value of each coordinate is bounded by 1. And I classify it. So the true hypothesis is the sign of the first coordinate. And then I trained with 10,000 random inputs in this box and classified with SVM. There's just a way to fit half space and I classify it with one nearest neighbor algorithm. And so what we see is the dimensions are 4 or 5, the first point, one nearest neighbor works quite well, but SVM works better. And then if the dimension grows, nearest neighbor is never more than 1/3, and random guessing would be 1/2. So nearest neighbor doesn't work at all. So it's not enough to have a classifier that works perfectly on the inputs. That works perfectly on the training set. Okay, I had to choose some parameter C and when I'm fitting hyper in sklearn, but it doesn't matter what value, the curves are very similar. So this SVM always works well. And we know from the theorem that as soon as we have for 100 dimensions, we need just a bit more than 100 input samples to get pretty good test error according to theorem. Okay, so the two conclusions that if the true classifier is a half space, then we need very few inputs to generalize well on test points. If it's not a half space and dimension is small, then one nearest neighbor might work. Okay, and then we can actually understand pretty well why in this example one nearest neighbor works poorly. So to explain it a bit more clearly, I changed the data. Instead of taking inputs from a box, I just take again hypercube with 0, 1 coordinates. And the label is again the first coordinate. And then the data is a little bit better because the task is easier. We don't have points near the decision border anymore. So the points are always on the side of the box if we compare with previous model. Okay, so and now we see that SVM makes 0 errors always in this model, so it even gets better. But our main question is why is one nearest neighbor algorithm so poorly? Because it looks very compelling. We know it makes 0 error on training set. It can fit any model, but then we use it. It doesn't work in practice. And the reason is it can fit any model given enough data. And the convergence is way too slow. So the first algorithm converges much faster. So if you want to understand what's a good algorithm, it's all about how fast does it converge for a test point. To a good function for test points. Okay, so but let's think a bit more. What is happening with the nearest neighbor algorithm? And so it's based on the distance between a test point and the closest point in the training set. So let's fix a point in the training set and look to the distribution of this distance. So this distance, it's written the value d you see there. And so there is indicator function in square brackets. So there are d terms, and the first term is informative. The first term will be 0 if the point gives a correct prediction, and 1 if the point gives a wrong prediction. But all the other points, they are noise. So all these other terms, they are unrelated to the label. So what we see in the distance, there is, for a fixed point, there is a contribution from the first coordinate, and then a huge amount of noise. So if we have just one training point in our training set, then there is only a small correlation. Because what we see here, D has binomial distribution, right? So it is a sum of Bernoulli variables. So you know very well it converges to normal distribution. So actually any sum of independent variables with bounded range converges to normal distribution. We will speak about it again many times, and you're probably already bored from probability course about this, but it's very important in all areas of mathematics. So it's unavoidable. No, but it's pleasant. Yeah, it's not a disaster. Okay, so yes, so we know that the variance is like square root, well, not the variance, the standard deviation is like square root. Okay, variance is proportional to d, while the useful information is just 1 that goes up top to the variance. And so 1 point is not informative. When we take the minimum of a few points, distribution will be similar. But to proving this, we need a few extra tools, which we learn in the 6th lecture or something. Okay, so here is a Galton board. What happens if you take the sum of several binomial variables? And this is not so important. Okay, yes. So only if the training set is exponential, then if you're like close to seeing every possible input, then this argument breaks down. So there will be again a Chernoff-like bound. On the excess error above 1/2. Okay. Well, now we understand that that overfitting is important problem. If we can beat this, this will be already well. Actually, there is nothing more to understand. So it is the only thing we need to. Okay, this is very vague statement. So let us try to understand it a bit more philosophically. So just think that in the daily life, there is some tournament with 20 games where 2 teams play against each other. There is exactly 1 winner in each game, and like football contest or whatever. And then before it starts, you get an email with prediction of outcomes on first 10 games. But of course, you get so many spam, you don't pay attention to it. But after 10 game, you again get an email and to say, please look to your old email, check the predictions, and you check it and it's all right. And then they say, okay, for 1 ruble, you can get the next 10 predictions. And then there's gambling houses or this website, I forgot the name, where you can gamble 50-50 odds. So you can take 5,000 rubles. And if the next 10 predictions are right, you end up with 5 million rubles, more than 5 million rubles. So it might be this 1 ruble investment of this guy might be useful. Okay. So, will you do that? What do you think? It's kind of fishy. So, okay. Now, yeah, so something else might, like, I don't know, if you have money and you play on the stock market, you listen to some YouTube movies about guys who gamble professionally on the stock market with the rich people's money, and they make a sequence of predictions. And then if one of these predictions is true, will you watch again and then play with your own money to this? So this is a more realistic setting. And then you see that this guy has several millions of views whenever he streams something. So then it's kind of interesting. So yeah, and then if he's right, then maybe it's a good idea to follow his advice. Well, okay, I'm now advertising gambling. I should not advertise gambling, but okay, so there are other considerations, but at least now you can pay attention. So what's happening with these scam mails? So it can be that a friend tells you that he also gets scam email, but his predictions were not right. So a strategy is to if you have 1 million email addresses, divide them into 1,024 groups, each send them different predictions, and the guy who's right, you can send a reminder and ask for money. So, and then, okay, whatever you pay for the next prediction, it has no value. And so this can happen in machine learning. So what is this nearest neighbor algorithm is doing is just selecting a hypothesis consistent with the data, but it has no predictive value because it will select it will always. So a priori, you have all possible distributions. It will select a distribution that's consistent, and it's not clear whether it captures the real structure. You might be lucky in low dimensions that there is some smooth geometric border and you capture most of the structure. But in high dimensions, probably going to be a problem. Okay. So this similar, more practical thing is fitting decision trees. So if you have some input data and you find a surprisingly small decision tree that's consistent, then this decision tree might have predictive value. And so there's the goal of second part of the lecture is to say something about decision trees in the online mistake model, to see this effect in operation. This contradicts what's happening in neural nets. So your machine learning teacher will say, the more parameters you fit, the better. The bigger your model, just don't blow up your GPU or CPU, just try the max you can get out, it will be better. And so it's contradicting the theory at when you look at high level. But actually, when you look at lower level, one will see that this learning algorithm is stochastic gradient descent. And neural nets will predict according to very specific hypotheses. And these hypotheses that are likely to be selected can be understood mathematically. And there is a way to transform this theory to SVM theory, the theory of fitting half spaces. So we will explain this, but this will be the last 2 lectures of the course. So that's why I start now, so that I don't need to drop the 2 last lectures. Okay. So, okay, I will skip to save some time. There's some more philosophy. So in history, so there are 3 types of learning: reproductive learning, where you just remember the training set, like nearest neighbor algorithm, but no generalization. Then in statistics, there is like rule-based learning. And then in the 80s, there were recommender system. And then we want to have a third type of learning where we define certain types of structures and put it in some objective function and then optimize it. But this is usually computationally intractable and be hard problems, so we need to do something to get reasonable results. Okay, I mean to have actual algorithms. Okay, and so how will we approach? We will make bounds on the performance of a training algorithm or of a learning algorithm. And so all these bounds, they are the sum of 2 terms. So there will be the sum of error on training set and some overfitting term. The more complex is our model, the bigger will be the overfitting term. But also the smaller we can make the error on the training set. And so our error on test set is sum of these 2 curves. So there is a sweet spot in the middle. This is classical theory, but for neural nets with gradient descent and a few other places, this doesn't work anymore. And so the error will drop again from certain point on. So this is called double descent. Okay, so then there is a question. Okay, the complexity depends on various hyperparameters from your model. Then you need to select them manually. So a common method is to use cross-validation to fit the hyperparameters. So in statistical learning theory, there is an abstract approach. You can avoid cross-validation because it's expensive. It means that you change the hyperparameters and you retrain everything. If you have more than 6 parameters, it's often hopeless. So you want to estimate them somehow. And in theory, the statistical learning theory can provide answers. And we will see that two important algorithms, so support vector machines and AdaBoost, can be understood as implicitly making such a trade-off between complexity and error. So it's one of the outcomes of last part of the course. So this is for lecture 8 and 9, 9 and 10. Okay, we will see. Okay, so this is overview of course. So, sorry, 3 lessons on online learning, 4 lessons on risk bounds without any assumption on the distribution. Then we will use margin assumption to get to classifiers, but we modify the theory from part 2. And part 1 is a simple version of the theory that happens in part 2. So I just explained the same thing over and over again, but each time a little bit more complex. This is opposite what other people do. They directly go for part 3, but then it's very technical and it becomes boring because you don't know what are the real ideas. If you see small changes, I think it's much nicer.
Where is the fourth lecture is about in the part 2?
Yeah, it's about neural nets. So what I just explained. So why neural nets have many parameters, but are still fitting in some sense a simple model. And to enhance this effect, you should take more and more parameters. But this is a recent theory from the last 6 years. But 4 years or 3 years it was ignored, so nobody knew about it except some weird researcher. But now it's generally understood. Okay. Well, let's start with the real stuff now. Online mistake model. So there will be 6 steps in the lecture. Maybe we don't have time for last step. So these are old slides. So I will always use D for dimension and N for the size of the training set. But here N is used for dimension. So, but it's only place I for trouble with the source code of the slide. So it takes a long time to update. Okay, so what's online mistake model? So just think about you have various websites. I live in Belgium. It's like France, Germany, Holland. So if a country predicts the weather, they can with the same effort do it for the countries around them because they need the weather of other countries to predict. It's all connected. So so we check all these websites, and some of them are sometimes they're right, sometimes not, and so can we aggregate from these? So what we want to do is predict as well as the best website, but when we start our predictions, we don't know which website is best for specific location. So now you can think that each website is a classifier, and then it gets like this the state of the current state of weather, and then it predicts the weather for the next 3 days, or for let's say good weather or bad weather, and then you decide to go outside or study or what. Okay, so you get it. So here in the model, so there is a challenger and a predictor, and then a supervisor that controls the process. And so what happens is in the beginning, challenger chooses a classifier from a set of classifiers. And then there are just rounds after each other. So a challenger chooses an input, then predictor makes a classification, and then the supervisor tells whether this is according to the secret function from challenger. And then it's repeated. And so here, if we run this forever or for a finite amount, or okay, let's say run forever, we can have repeated input if x is finite. Then we end up with a number of mistakes. And so the question is, does predictor have a strategy to make a guarantee that number of mistakes is bounded by a certain value? So let's do an example. So let's think about binary inputs. So dimension with n dimensions, and the algorithm is predict according to the smallest coordinate for which projection is consistent with labels, for which projections equals all the given labels at some point. And so our hypotheses are the projections on the bits. So the labels, so inputs are bits 0, 1, labels are also 0, 1, and we want to learn the correct projection that's used. So we predict according to smallest consistent projections. For example, let's do a game. So we have 3 dimensions, we receive 0, 1, 0, and we predict whatever, anything now. So we, so all projectors are consistent, so we follow the projectional first coordinate. So we predict 0. And then we receive the answer, and it turns out the true classifier might be 3, so then our answer is correct. So the set of consistent classifiers is called version space. So important concept. And so now version space is 1 and 3. So now we receive 1, 1, 0, we predict 1, now we make a mistake. And version space is F3, so from now on, we are always right. Yeah. Sorry. Yeah. So the true classifier is projection on third coordinate. Yeah. So we predict 1 in the second example because it's first coordinate. Yeah. Okay. So so now is the question, if we have n dimensions, what is maximal number of mistakes that we can make? So what the maximal number by this specific algorithm? Yeah, exactly. Indeed. And so what can happen? Well, here, n-1. So here is the example. And we make sure that every prediction is wrong, and we can do it n-. And each time the version space loses 1 function. But the true function is always in version space because by definition, it's always consistent. Yeah. So this is tight bound for this algorithm. So now, yeah, we can generalize this algorithm. Always, so for any set of hypotheses, always predict according to the first consistent hypothesis. And so on the top, we have a theorem that mystic bound. So mystic bound of a set of classifiers is maximal number of mistakes by the best algorithm. And so mystic bound for algorithm is the largest number of mistakes it makes against any strategy of challenger. And so we take the best challenger and we look to how many mistakes are. So we look at worst case bound. And then the mystic bound of a class of hypotheses is mystic bound from the best predictor. And so predictor that works best against his worst case opponent. And so we've proven that if we have a finite set of classifiers, then mystic bound is always at most size of classifiers -1 by the previous algorithm. But we can do better. We can have a bound given by binary logarithm of the size. So it's called halving algorithm. So maybe you can guess how it works. It's it's a difficult question. So I just tell you. So we will take majority vote. So what happens when we receive an input? We look to our current version space and take majority vote of the predictor's inversion space. And so now we understand why number of mistakes is logarithmic. So initially virtual space is all classifiers in H, and at each mistake, we lose at least half of the version space. Version space decreases by half. And the true function is always in the version space. So version space goes from size of H to 1. And we can have at most M updates. The log of size of H updates. Okay. So what is in our first step? We defined online mistake model and proved logarithmic bound on the size of hypothesis class. Okay, let's go to second step. So there are instances where number of mistakes is unbounded. Cases are, sorry, I have 25 minutes, okay. So there are two examples. So first example, what happens if we take the set H to be the set of all classifiers? Let's say, say for example, that we have infinitely many inputs and we allow all classifiers. Then the mistake bound of this class is infinite. So why is it? Okay, so let us think about the game. So first challenger has to pick a hypothesis. Now before, which hypothesis should we pick? Okay, let us think that, so predictor applies a fixed strategy. Now let us play a bit with the strategy. So let us apply the strategy to the same game, but we don't fix the challenger. So the game is played in rounds, and the choosing challenger's first choice of function is secret. So doesn't affect prediction of behavior of predictor. So we can just run all the rounds and just for fun say that each time to the predictor wrong, 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 wrong on all different inputs. And so we just take we look to the input space, iterate over all inputs, listen to the predictor, and each time say that predictor is wrong. Okay, so this is the game. So let's let him say failure all the time. So after we do this, we get inputs for a bunch of functions. And since we have our hypothesis class is a set of all functions, we can take the opposite of all the predictions for the true function. And if we give this function, if challenger chooses this function in the beginning, then he has exactly the same answer, and predictor is always wrong on this function. So here, infinitely many mistakes. If we have finite input space, then number of mistakes will be size of input space. And so here is general principle. So if we make a performance bound that works for all the classifiers, for all classifiers without restriction, then this bound is meaningless. This bound is as good as any classifier that just remembers previously seen inputs. So this is a restriction. This is the reason why when we make performance bound, we will always make an assumption on the true distribution. So here we work in realizable setting where there is a true distribution. In machine learning, this is too strong, so we will weaken it later. But for now, let's start with this assumption. But actually, we will, okay. So now the next question. What about half spaces in the online mistake model? And so it doesn't work very well because even in one dimension, predictor can enforce infinitely many mistakes. So this is easy. So so we're learning thresholds, right? So we have one input, a real number as input. Above this number, we predict plus, otherwise we predict minus. Okay, and now we can construct in a very similar way a function in which so for each predictor we can construct a sequence of inputs where predictor is always wrong. And so we just start with any point x1. We listen to answer of predictor. He says -1. So then we will commit to having our threshold on the other side of the input. And so here it's on the left side. And then we can repeat. So now predictor will ask about another point. So we choose, so now the version space, so we commit to a version space at the left of x1. So we drop the right of x2. So then we take a threshold in the version space and repeat the process. And in this way, we guarantee, so the points will converge to some point in the limit. And this will be our threshold that will make this predictor to be always wrong. So we see the model doesn't work for learning thresholds. And so our solution, just in the third step, will be, in the last step of this lecture, will be to apply a margin hypothesis. We will prevent inputs that are close to the true threshold. And then this convergence will stop after logarithmic number of steps. Okay, but first, before we do this, we will consider, so there is a small technical lesson. So we will now go to overfitting of decision trees. But for this, we need to understand how many decision trees there are of certain size. So the number of decisions, so here is the question. How many decision trees are there that have k nodes and classify and with inputs? So decision tree, you already know this. I mean, okay, it's very simple thing. So when you go to doctor, he asks you a bunch of questions and don't tell you whether you have a certain disease, yes or no. And so in this model, our inputs will be bit factors. So every patient is identified with a set of answer on possible questions. So if there are n questions, then you're in n bit string for the doctor. I mean, according to this model, yeah. Okay. And so when we count k, so T and k is set of decision trees with n inputs, k nodes, and leaves are included. Oh, I didn't try. Okay. So this tree, it has 3, 7, 9 nodes, 4 leaves and 4 other points. Sorry, 8. No, 5 leaves, 4 points. Okay. And so how can we bound the number of decision trees? Each decision tree, we will give a description. So different decision trees should have 2 different descriptions, but some descriptions might not have any meaning. And then we bound the number of decision trees by number of descriptions. So what's description? We just iterate in that first way through the decision tree and make a list of the leaves. And so this tree we can write as a list by writing, so an internal node corresponds to a question, so coordinate. So whether we write the coordinate or the answer of the leaf. And so here we go in that first way. Here is the answer, then we backtrack and so on. So since you're all computer scientists, this is quite clear. Yes. So we start with the root. So we do that first. Yeah, so in the root, we ask about the second bit. So X is the input and X2 is the second bit. Oh, yeah. Yeah, thank you. Yeah, and I should clarify notation. Yeah. All right, okay. Yes, and but if we have a correct list, then we can reconstruct the tree. We know the first element is the root, then we go to the left leaf, again its left leaf, and so on. Okay, we could do breadth first way as well. It doesn't matter. Yeah, I think. Uh, okay. Okay, now we identify trees with lists and we know how many lists we can have. So number of lists is input dimension plus number of labels. So input dimension plus 2 because we will usually have binary classification. Okay, and now we can apply this to our halving algorithm and understand that if there exists a small decision tree, then we are guaranteed to make small number of mistakes. So if there exists decision trees that make 0 errors on a hull over sequence, then our algorithm, who doesn't know this decision tree, will find it after few mistakes. K log n plus 2 mistakes. Okay, so now, okay, this is completely impractical algorithm. I just wrote this as a way of introduction. So it's clear that to learn K nodes, you cannot afford to, if K is 100 or something, you cannot afford to have 5 to the power 100, like brute force all these things. So, okay, but this is nice if we know K. What if we don't know K? Then we can modify our algorithm a little bit. So a naive approach. So this is our third step of the lecture. And 15 minutes left, so we might make it. Okay, so what if we don't know K? So I claim that we can do a little bit better instead of logarithm of size of decision. So we just have to add 2 log K plus 1 mistakes if we don't know K. Okay, what might be naive approach? We can start with the value K equals 1 as version space, and then continue halving algorithm until the version space is empty. And then we fill version space with T and 2. Okay, that doesn't make sense. And 3 is the next non-empty one, and so on. And then number of mistakes will be quadratic in K. So, but we can do something better as promised. And the plan is to assign weights to the classes and then take weighted majority vote. So this is your weighted halving algorithm. So our plan is to use the weights for the class is 1 divided by K divided times K plus 1. And so the sum of these weights is 1. So if we sum this over K, this is 1. And so each classifier to get the weight of a decision tree, we use the weight of the class according to size, and then divide by the size of the class, or divide by upper bound on the size. Okay. And now we take weighted majority vote according to predictions. So here I use the labels -1 and +1. So you can see between the boxes labels -1 and +1. And so what do we have in the predict line at the bottom? So what do we have there? So the trees that predict +1 will have a positive sign in the sum. Those that predict minus will have -1. And those with the largest weight, so the group with the largest weight wins in the sign. So a sign of 0, so in machine learning, sign of 0 is usually taken +1. It doesn't matter what you take, but convention is +1. Okay, and this works for exactly the same reason as the previous halving algorithm. So what changes in the proof? So I have written this. So in top the same algorithm, And so let's look to the total weight. So initially the weight diversion space is the set of all decision trees, and its sum is 1, or at most 1 if you. Okay, but let's count representations of decision trees according to the list, and then the sum of weights is exactly 1. Okay, and then each time that we make a mistake, we know that the weight of the version space must decrease by half, because we drop the larger part of the weight. But we know that the correct hypothesis always is in the version space. So the weight of version space goes from 1 to the weight of correct classifier. So this is what's written here. And we know that if K is the size of correct classifier, then we know version space will always be bounded by this thing. So when we take negative logarithm, we see that upper bound for M is 2 log K plus 1 plus log of size of H. Okay. Okay. And so this finish our conclusion. So if we know K, number of mistakes is K log N plus 2 at most. If we don't know K, it's essentially the same. But again, completely useless algorithm. Don't even bother to implement. Okay, so now let's go. We assume that in our training data, we had a model in our hypothesis that it's always correct. Let's drop this assumption, which is, so it's called realizability assumption. But usually in machine learning, this is not used, this assumption. It's more for theoretical computer science and study learning questions. Okay, so in the weather example, there is no forecaster that's always right. It's a very realistic assumption, depending on the time frame of prediction. Yeah, but even for, yeah. Okay, let's not speak about weather. Okay. So, fine. Okay. So now we will assume that there is in our model at least one predictor that makes few mistakes. Let's say M mistakes. And the question is, can we have an algorithm that doesn't know which model is correct, but makes also close to M mistakes? And the nice result here is that we can get close up to constant factor in this model with deterministic algorithm. And so the first observation is, but it's in the seminar. So the best we can do is number of mistakes bounded by 2M. So there is an upper bound. There is always a challenger that enforces 2M mistakes. It's kind of for very simple reasons, but it's like when you know why, you think, of course. But now it's mystery. Yeah. So it's Nikita will bring you to the solution. And so by choosing beta close to 1, we can get arbitrarily close to this factor 2. But it's for deterministic algorithm. For probabilistic algorithms, you can something with square. I forgot at the moment. You can do much better. So you can have M plus square root mistakes. So order square root of M mistakes. Yeah, and then something with the size of H. Okay, so let's prove this theorem. So I first need to say what is the algorithm. So note that in the previous model, when a predictor, when classification function is wrong, we drop it from the version space, never consider it again. But here we can never do this. We can have a classifier that's always wrong, but then even gets the same inputs again, but now it's right. Because we no longer assume that we have no assumptions. So here is a theorem. We have no assumptions on the input space, on the training data. The same input can be with both labels. Okay, so that means that a function that's wrong in every turn in the beginning might end up to be the best function later. So we never discard classifiers. But what we will do is we will give them a weight and we decrease the weight of classifier if it works poorly. So here, so now we have weights that depend on classifier and the round. And in the beginning, we set them all equal to 1. And then we go through the rounds. So we receive an input. We make a prediction according to weighted majority vote. And then we receive the correct answer. Okay, after receiving correct answer, we update the weights of all classifiers in the hypothesis class. So we decrease it by factor beta, beta strictly smaller than 1, but non-negative. If we set beta equal to 0, we have exactly the halving algorithm. And then we discard, we set the weight to 0, it means discarding class. Okay, so now why it works, and okay, it's almost the same proof. So here is algorithm again with the proof below. So what happens when we make a mistake? Again, majority of the weights is in classifiers that are wrong and their weight decreases. But now not to 0, but to beta. So the hardest part is to understand the first inequality. How much do the weight drop? So all the classifiers that are wrong lose fraction beta. And we know that at least half of them are wrong. So the weights, the total weight, sum of weights gets multiplied by 1/2 plus beta over 2. Okay, it's you need to think a little bit. So you just have two terms, the good classifiers, the wrong classifiers. So the exact expression of the sum of weight is weight of good classifier plus beta times weight of bad classifier. Let's rewrite the weight of good classifier, 1 minus weight of bad classifier. So now the factor of bad classifier is -1 plus b. So we use a lower bound on the weight of bad classifiers, which is half of the good classifier. Okay, I should write, but there are some markers here. There are two people offline. Well, let's not waste time because the lecture needs to finish. So please, homework. If you don't get it, work it out. Okay, then we get to the second classifier. So if there exists a classifier that makes m mistakes, we know that the final weight will be at least beta to the power m, because this classifier starts with weight 1 and only loses in m rounds. And so we get these classifiers. And so now to get a formula in the top, we take negative logarithm. And so the only thing we have to do is so on the right, we have the sum of all weights. And this is just initially in the beginning. And we set the weights in the beginning equal to 1. So at the right, we have size of hypothesis class. And so after negative logarithm, we just have to divide by logarithm minus logarithm 1/2 plus beta over 2. And we get the formula in the top. Okay. So now we can define the agnostic mistake bound. So that's what we've been studying for a given class. So it's a minimal number of mistakes that the best classifier makes against its worst case challenger on inputs for which h for which best result of H classifier is at most M. Okay, let me say it again. So in this definition, which input sequences do we consider for a fixed value of M? So these are the input sequences for which there is some classifier in H that makes at most M mistakes. Okay. So now we will look, so what is the bound for a fixed prediction algorithm? It is worst case number of mistakes by prediction algorithm on such a input sequence. And what is mistake bound for a class? It's the bound for the best predictor. So it's just a thing we've been studying all the time. Best predictor against his best challenger. But now we restrict to input sequences where best classifier of H makes at most M mistakes. So when we set M equal to 0, then we assume there is one classifier in H that makes 0 mistakes, and we are back in the previous online mistake bound for the realizable setting. Okay, so getting a bit tired, but there's only one part left. I had, okay. Oh yeah, then we can, oh, sorry, something important. Let's apply our theorem to decision trees again. So then we know if a tree with K nodes works, we can replace size of H by K log n plus 2. So what do we have? So let's fix beta equal to 1/2. And then the denominator is 1/4 or something. So we have this mistake bound. And so we can rewrite, we can replace the size by this, and this is our mistake bound. And here we see complexity, bias complexity trade-off. So when we increase the size of K, the size of the decision trees that we fit, we probably find better decision trees, and the error on during training number of mistakes becomes smaller. I mean, this value of M that to which we apply definition becomes smaller because best tree makes fewer mistakes when it's bigger. But we have this 4K log n plus 2 term is kind of overfitting term. By taking more decision trees, we error also increases in this algorithm. So here we again have this bias complexity trade-off. Our bound is the sum of two terms, error during training and overfitting term. So error of best model plus overfitting term. Okay. So what can we do if we don't know K in advance? And it's either in the seminar or the homework. I forgot where I put it. But okay. So yeah, conclusion. We have this mistake bound. And we had the first time we have a specific bias complexity trade-off for size of the set. Okay, and I will go few minutes over time. There is one little topic, but yeah, we started, there were some, yeah, I was late, okay. Yes, so so the last part is how we learn half spaces in the online mistake model. So, so let us remember, we even in one dimension, we make infinitely many mistakes. And our plan was to have a margin assumption. So, okay, no, it will take too much time. I will stop here with the lecture. So, sorry, yeah. It's just one exercise in the seminar, and either Nikita can explain this part if but probably you will not. Okay, we will. Okay, so yes. So next lecture I will explain optimal model and the realizable setting for online mistake model, and then we will in detail explain perceptron algorithm. So several versions. There exists a dual algorithm. Okay. So see you in 2 days. That's it. Wait, I stopped. Okay, so the link should be on the wiki for this.